Good morning, everybody.
Good morning.
Good morning.
Okay, so the plan today is to start talking about Chapter 6, which is electromagnetic waves and electron configurations. Any questions? Any problems anybody wants to look at to get started?
Good morning.
Good morning. Okay. So I'm going to go ahead and start on Chapter 6 then, and we'll start talking about electromagnetic waves. The focus of this chapter is really to lead us into discussing the elements. So for example, the difference between hydrogen or oxygen or iron, and then to lead us into covalent bonding. So that we'll start looking at covalent bonding in Chapter 8. But we begin by looking at how it is that we're able to study the atom. All of that we've looked at so far, Chapter 3, 4, 5, and 10, have not looked at the level of the atom. We would weigh out a certain amount of something, look at how much reacts with what, measure the pressure or the temperature of a gas, but nowhere in that are we actually looking at what's happening at the level of the atom. And that's what we're going to do here. We're going to look at the level of the atom. The discovery and understanding of the structure of the atom is still ongoing, but is quite an accomplishment for humanity to understand what we're made of at the lowest level of structure. So let's talk about the way that we study the structure of the atom, and that is by using what is called electromagnetic waves. Okay, you are familiar with electromagnetic waves. The most familiar one is what we call visible light. And visible light is what we use for eyesight. But you're also probably aware of it's hard for me to pronounce it, infrared radiation. It is sometimes referred to as IR. If you've ever seen night vision goggles, the image that you get from that, that's based on infrared radiation. There are also what are called ultraviolet waves or ultraviolet radiation. We call that UV, right? These are the damaging rays that can cause skin cancer. And also medical imaging uses X-rays. And there are some even more exotic types of imaging techniques called gamma rays, or using gamma rays, and methods of killing cancer cells, gamma rays. And then there are also radio waves. So radio waves are used for cell phones, AM radio, FM radio. We use it for communications. And we also have what are called microwaves, which are also used for cell phones. Sometimes we use actually, let me put a little symbol there. That's the symbol mu, which is often used to refer to microwaves. Gamma rays also have a type of symbol, a Greek letter, the Greek letter gamma, lowercase. And microwaves are also used for cooking foods, right? Essentially what happens is microwaves have enough energy that they can cause molecules to vibrate. And when the molecules vibrate, water molecules to vibrate. And when water molecules vibrate, that essentially heats up the food. Okay, so these are all examples of electromagnetic waves. We'll use a very simple word to refer to them. We'll call them light. Even though in everyday life, when we say light, we really mean visible light. We'll use light as a sort of shorthand notation for all of these different electromagnetic waves. Okay. So these are what we use to determine the structures of molecules. It's what we use to determine the structure of atoms. Okay. So radio waves are used in MRI, magnetic resonance imaging. Okay. Ultraviolet and visible light are used in what's called, actually all three of these are used in what's called spectrophotometry. So that's used to determine the structures and to determine even amounts of materials. So for example, if you're doing urinalysis and you're trying to find some particular compound in urine, spectrophotometry is used to determine the concentrations of solutes that are dissolved in urine or blood for that matter. X-rays, of course, are used in medical imaging. And gamma rays are not used as much in imaging yet, at least not yet, but they are definitely used in terms of killing cells. Okay, so cancer cells, for example. So pretty much all of the different forms of electromagnetic waves are used in different medical fields now. I mean, that shows kind of the power of understanding how they operate. Many of them are also used in terms of communications, microwaves, radio waves, ultraviolet, not ultraviolet, infrared, visible light now. Those are all used in communications, cell phones, satellite communications, stuff like that. Okay, so let's take a look at these electromagnetic waves. And the reason that most of them are used in the medical field is because humans are constructed of atoms. We're made out of atoms. So these types of waves are able to interact with atoms, and that's what allows us to determine certain aspects of our structure. Okay, so let's take a look at waves in general. Waves behave very differently from what we think of as particles. So for example, if you drop a little pebble in a lake, for example, what you'll see is that over time, the water on the surface of the water will get disturbed. And you'll see these concentric circles moving out from the source. This is called a source, where you drop the pebble. And what's happening is essentially the water is moving, right? That disturbance is occurring. This is really what we would call a transfer of energy. The kinetic energy of the pebble hitting the surface of the water has caused the water to move outward in these circles. And what you'll look at, if you take a look at these circles and you turn it upside down, or at least onto its side, what you'll see is that the water has a structure. This is the surface of the water. So in some places, the water is below what you would think of as the surface. So this is below the surface of the water. And in some places, it's higher. This is above the surface of the water. So you've created a wave. Essentially, you've created a repeating pattern on the surface of the water, and we call that a wave. A repeating pattern, I should say. Okay. Sometimes it's called an oscillation. And that's a water wave. Okay, so there are different types of water waves, right? There's the waves that crash on the beach, there's dropping a pebble, there are tsunamis, there's all sorts of water waves out there. Some of them travel fast, some of them travel slowly, but they're all what we would call disturbances. It's also interesting that waves possess energy. That's an important aspect of it. All waves have energy. It's just a way in our universe that matter is able to transfer energy. So think of an earthquake, for example. That's really a vibration, an oscillation, a repeating pattern in the crust of the earth. So it's a way for the earth to transfer some sort of frictional energy as the parts of the crust are actually colliding with each other, and then it transfers energy out in the form of an earthquake. Okay, what we're interested in, oops. There we go. What we're interested in are what are called electromagnetic waves. These are a very particular, specific type of wave, and they're very interesting. And so let me say a couple things about them. One is they travel through space. Okay. There are waves that don't actually move anywhere. They vibrate, but they stay stationary. Those are called stationary waves. But these are what we call traveling waves, which means that they move from one point to another. Okay, like a light bulb, right? The source of a light bulb, the source of that light is the light is traveling through space. Okay, they travel at we would consider a pretty fast speed, a pretty high speed. And so just to be technical about it, in a vacuum, meaning like we're in outer space, the speed of these electromagnetic waves, we're going to use the symbol c. C is traditionally used as the symbol for the speed of a wave. If you're talking about the speed of a car, you might use the symbol v or s or u. Your textbook uses a u. But for waves, we use the symbol c. The speed as you travel through space, I'm not going to get it exactly right, but it's, let me see if I get this right, 2 or close to right, 9979. Okay, let's do 10 to the 8. So what is that? 4, 5, 6, 7, 8. Did I get that right? 4, 5, 6, 7, 8. Oh, I'm off one too many. Sorry. Four, 5, 6, 7. Wait a minute. Let me see. Let's get that right. This would be, actually, that would be 3. So I was right. I was closer the first time. Sorry. Let me do it this way. My counting is not going very well. So let me put it in scientific notation. Okay. I'm going to put it in different units. Okay. So now let me do this. Let me do this one up here. I was struggling with that. So let me take that number. This is meters per second. And let's put it in decimal notation. The way you put it in decimal notation is you locate the decimal point, and this is 10 to the 8th. So if I move it to the right, 1, 2, 3, 4, that would make this smaller by 4, but I want to get rid of I'm trying to get rid of the powers of 10 just to put it in decimal form. So I've gone 4, so I got to go 4 more. So I got to add 4 zeros to get rid of that 10 to the 8th. So it would be 29979. That gets rid of the first 4, but we got to do 4 more. There we go. So now, there we go. So that's 299,790,000 meters per second. This is meters per second. Okay, that is approximately the speed of light. In kilometers per second, it's 2.9979 times 10 to the 5th meters per second. I just divided it by 1,000. So that's pretty large too. In miles per second, it's 1.86 times 10 to the 5. So that corresponds to 186,000 miles, not per hour, but every second. And so just to put that into perspective, if you look at the Earth and you compare that to the moon, the distance, the average distance between the Earth and the moon is about 238,000 miles. Okay. That means that if you turn on a light on the Earth and the light waves move toward the moon, they move at a speed of about 186,000 miles per second. So if you take 238,000 miles and you multiply that by 1 second per 186,000, you get about 1.3 seconds. So that's how long it takes for light to travel between the Earth and the moon. The sun is much further. It actually takes around, I think it's around 11 minutes from the Earth to the sun. Okay. So the speed of light is very, very fast. We call it the speed of light. Speed of light. Okay. The symbol for it is a C. And what you want to remember is that this speed, it doesn't matter. It works for all electromagnetic waves. Okay, it works for all electromagnetic waves. So I'm going to make a list. I made it already, but I'm going to give you a list of electromagnetic waves. And I'm going to start on the left side here. I'm going to start with radio waves. And then I'm going to go in a particular direction, and we'll talk about the direction that I'm moving a little bit later. These are called microwaves. Infrared. These are all waves, and sometimes we call them waves, sometimes we call them rays. Visible light. Ultraviolet. Radiation, we call it radiation. Then you get X-rays, and then you get gamma rays. So those are all the different types of electromagnetic waves. And what I'm going to claim is that they all travel at whatever this number you want to write it as, 2.9979 times 10 to the 8th meters per second in a vacuum. They travel a tiny, tiny fraction slower through air, but it's pretty much the same number. It's not that different. So we'll use the same value if they're traveling through air. Okay, these are all electromagnetic waves. And I'm going to give you a couple of aspects about them. One is energy. So let me talk about energy. If you move in this direction, you're moving towards increasing energy. Okay, So what I mean is gamma rays have more energy than X-rays. So I'm going to write over here, these have the highest energy. And radio waves have the lowest energy. Okay. So one aspect of this that's significant is that ultraviolet radiation, UV radiation, can cause cancer, whereas visible light, for the most part, doesn't. And the reason for that is that ultraviolet radiation has more energy. In fact, enough energy to break chemical bonds. So if you can break a chemical bond, you can break the chemical bond of a DNA molecule. And if you can break the chemical bond in a DNA molecule, you can disrupt the division of cells, and then you can develop cancer out of that. So in a sense, once you get right about here, that's when you can start breaking chemical bonds. From here to here. X-rays, gamma rays, those are capable of breaking chemical bonds. The ones down here, radio waves, microwaves, infrared, and visible light, they do not have enough energy to break chemical bonds. Okay? So those are the, what are there, 7 of them? 1, 2, 3, 4, 5, 6, 7. From radio waves to gamma rays, those are the 7 types of electromagnetic waves. And those are the 7 you should be aware of. And you should also be aware of the fact that the energy is increasing as you move from radio waves to gamma rays. So if the question were, which has more energy, visible light or microwaves, the answer would be visible light. It's further to the right here. So visible light has more energy. Okay. Now let's talk a little bit about visible light too. Visible light, because we use it to see, we are very sensitive to visible light. We can tell really minor differences between visible light. And we perceive this as color. And we'll talk a little bit more about that in a moment. But there are a few colors that we can see. So I'm going to start by putting ultraviolet here. Remember, we're going to increasing energy here. And then I'm going to put visible here. And then I'm going to put infrared. So I'm just showing you part of that, what we call a spectrum, part of all the different types of electromagnetic waves. So here's infrared. Again, this is increasing energy to the right. Okay. What I'm going to do now is I'm going to take this visible light and I'm going to break it out into several colors. We'll call them the primary colors. Okay. And the colors are red, orange, yellow, green, blue, indigo, and violet. The indigo and violet, sometimes we perceive them as purple, sort of a purplish color. Okay. This order can be memorized. The famous way to do it is the name of someone, Roy G. Biv. Roy G. Biv. So that's the sort of an acronym for remembering the order of these colors. And I just want to point out that the red is closest to infrared, right? Infrared and then red. Those are right next to each other. So the order of this is it's infrared. And we don't really have names for the different colors of infrared because we can't see with our eyes. Because we have instrumentation that can measure infrared really well, we do have some names. We'll call it near IR or far IR or mid IR. but we don't have names like colors. We don't have labels in that way. But our eyes can see all these different colors, so we have labels for them, okay? So the order is infrared, then red, then orange, then yellow, then green, then blue, then indigo, then violet, and then ultraviolet. And it is important to recognize just how sensitive our eyes are to these colors. If you look at all these different types of waves, visible light is really just a small sliver of what we call this entire spectrum of electromagnetic waves. It's really a tiny sliver of it. But because our eyes are so sensitive to that type of light, we actually conceive it, we can perceive it, and we can perceive even different colors of it. Okay. So in terms of energy, remember, infrared is on this side, so this is less energy. And then ultraviolet was over here, so this is more energy. So the order of energy with the visible light is you start at red and you go all the way to violet. So this is increasing energy here. So that means that red light has less energy than orange light has less energy than yellow, and so forth and so on, all the way to violet. So violet, in terms of visible light, violet has the most energy. And then once you get beyond violet, then you get to ultraviolet, and ultraviolet has even more energy. So violet, really not quite enough energy to break chemical bonds. It's pretty close, but not quite. Ultraviolet, however, has enough energy to break chemical bonds. There are ways to get visible light to break chemical bonds, and there are some really weak chemical bonds that can be broken with visible light, but for the most part, it's ultraviolet is sort of the cutoff. Okay, so let's talk about two properties of visible light, or of light, sorry. Again, I'm using, when I say light, I mean electromagnetic waves. If I really want to talk about visible light, we'll actually call it visible light. But if I say the word light, I mean any of these electromagnetic waves. It could be radio waves, it could be ultraviolet, it could be gamma rays. And these two properties are called wavelength and frequency. And the symbol for the wavelength, is a Greek letter. You're going to see some Greek letters in this chapter. This is pronounced lambda. Okay, it's a Greek letter, lowercase. Lambda is what's used as the symbol of wavelength. And the units of wavelength are distance units: meters, centimeters, micrometers, nanometers. Those are just the metric prefixes, but distance units, so meters. Frequency, there are different symbols used for frequency. So just to be careful, sometimes people use an F, a lowercase f, for frequency. But sometimes people use the Greek letter nu. This is pronounced nu, N-Y-O-O, nu, okay? And this has the units of 1/seconds, which can be written as seconds to the -1, or hertz. And the abbreviation for hertz is Hz. So there's different units that you may be unfamiliar with for frequency, so you'll have to get used to using those units. So let's take a look at these two properties of light, of electromagnetic waves. So the first property, let's do wavelength. Lambda. What we said was that electromagnetic waves are waves, so they are disturbances. They are essentially repeating patterns. That's the idea of a wave. It's just a repeating pattern. So like the concentric circles on the water. So wavelength, I'm going to draw a little coordinate system here. This is the x-axis, and this is the y-axis right here. Okay, so notice this is general. This is the general form of a wave. Not all waves look like this, but the ones that we deal with in this course will. It's a sine wave, essentially. So it goes up and down and up and down and up and down, and it's got a repeating pattern. So this is called a peak or a crest. Some people call it a crest. This minimum point over here is sometimes called a trough. Trough is sort of the minimum there, okay? And so notice sometimes the wave is going through the x-axis. Sometimes it's below, sometimes it's above. If it's below, sometimes we would say that it's negative. So anything below the x-axis is negative. Anytime it's above the x-axis, it's positive. Okay, above is positive, below is negative. The distance vertically between the x-axis and the peak is called the amplitude. So here's the peak. Notice the amplitude is the same here because this is a repeating pattern. So the height of the peak is the same all the time. So that would be called the amplitude. Sometimes the letter A is used to refer to the amplitude. Now, on the x-axis, I'm going to make this distance. Okay, and I'm not going to worry about the units for right now. It could be meters, could be centimeters, could be micrometers, could be miles, it could be inches, whatever it is. The distance between two peaks, and I'm going to use these two peaks here just so that it's not too crowded here. This is called the wavelength. Okay, so let's define the wavelength. It is the physical distance. And these are length distances, right? I'm talking about length, how far something is between two adjacent peaks, meaning two peaks that are right next to each other. So again, think about that little water droplet. I'm sorry, the little pebble that we drop on a lake. What's happening? You get these concentric circles forming and moving. So the wave is moving away from the source, from where you drop the pebble. So the wavelength would just be how far these two are, right? Those little rings are, the little rings on the water. How far are those rings? That would be the wavelength, okay? Now, we can also talk about frequency. And again, the symbol I'm going to use is a nu, N-Y-O-O. And the frequency is time dependent. So now we're talking about time. So if you think about it, that wave is moving outward. There's some kind of time component over here, right? It doesn't just instantly move out and be all over the place at the same time. Over time, the wave is moving. So if a wave is moving, we can analyze it in terms of time. So I'm going to say the following. The frequency is equal to the number of peaks per given time. So how many peaks there are in a given time? Typically, it's per second. So it's the number of peaks per second. We could use other units of time, but typically we're going to use the second. Okay, so now imagine something vibrating. Okay, it's moving in time. If something vibrates in time, it has a speed And it also has a number of vibrations or a number of cycles every second. So we can just call this the number of cycles or vibrations per second. Okay, so that gives it sort of unusual units. A cycle doesn't have a unit, but time does have units. So what you end up with is 1/seconds. And typically this is written as s to the -1. Okay, 1/. But that's awkward. So if I say the frequency is 5,000 1/seconds, that's just an awkward way to say it. So we give it a name and we call it a hertz. And the abbreviation for hertz is Hz. So for example, we might say the frequency is 5,000 hertz. That's a lot easier to say than 5,000 reciprocal seconds, okay? But they mean the same thing. Now, one of the things that's interesting about these two variables, wavelength and frequency, is they're related to each other. And they're related by the speed. C, again, is the speed of electromagnetic waves of light. And speed is 2.9979 times 10 to the 8th meters per second, right? That's your speed. Any electromagnetic wave will move at that speed. Turns out the speed is related to both of them. The wavelength times the frequency. Very simple relationship. Okay, so remember, this number doesn't change. So that's a constant. So any calculation for the wavelength or frequency of electromagnetic waves, you've got a number there that you know the value. And then it's just the product of those two. So let me show you an example of how you can use this. Suppose I say let's use wavelength. The wavelength of X-rays used in medical imaging is 1.54 times 10 to the minus 10 meters. Calculate the frequency of these waves, right? They're X-rays, so they got to be waves. And if they are electromagnetic waves, they have a wavelength, which is some measure of how their distance, how big they are. And they have to have a frequency, which is a measure of how quickly they're vibrating. Okay? The relationship is very simple. C equals lambda times V. So if we want to know what the frequency is, we take our little equation here, C equals lambda times nu, and we divide both sides by lambda, right? Because if you divide both sides by lambda, now you just have frequency on the right side. Okay, be careful, this is not velocity. If we're going to use velocity, we'll use either a V or a U. But if we're going to do frequency, we're going to use a nu. Okay, so that means the frequency is the speed divided by the wavelength, right? Speed over wavelength. So 2.9979 times 10 to the 8th meters per second. That's your speed, divided by the wavelength, which is 1.54 times 10 to the minus 10 meters. So meters over meters, and you're going to get 1/seconds. But remember, 1/seconds is hertz, right? So when we write the answer, we might want to write it in hertz. So 2.9979 times 10 to the 8th divided by 1.54 times 10 to the minus 10, you get 1.94 or 1.95 times 10 to the 18th. Okay, so there's your frequency. So what that means is the size of an X-ray is 10 to the minus 10 meters. Imagine how small that is, right? It's essentially the size of an atom. That's why X-rays are good for imaging atoms and molecules, is because they're essentially about the same size. The size of an X-ray is about 10 to the minus 10 meters. We call that the wavelength. And then the frequency, how rapidly it's vibrating, is 10 to the 18th hertz. That means it's vibrating. It's undergoing an oscillation 10 to the 18th times per second. It's unimaginably fast. But that's the nature of electromagnetic waves. They have very, very high frequencies, high vibration rates, and they have very, very small wavelengths. At least many of them have very small wavelengths. So let's do the following. I'm going to compare this. I want to give you the whole picture here. I'm going to compare this to, let's try an AM radio signal. Now, unlikely do you listen to AM radio, but AM radio has frequencies that are around a megahertz. Okay, so there's a megahertz. Okay, let's write it in scientific notation. In fact, let me give you, we'll use 1.01 times 10 to the 6 hertz. Let's use that frequency right here, just to be a little bit more accurate. So there's a radio station in New York that uses that particular frequency to carry its signal. So let's calculate the wavelength for that particular wave. So C equals lambda times nu. If we want to know what the wavelength is, because we know the frequency, we would divide both sides by frequency. And that gives you your wavelength right there. So that means the wavelength here is, again, 2.9979 times 10 to the 8th meters per second. It's not useful to use miles per second. It's just we don't use those units. 1.01 times 10 to the 6th hertz. But remember, hertz is 1 over seconds. So that way seconds cancel and you get meters. Okay, so 2.9979 times 10 to the 8th divided by 1.01 times 10 to the 6th, and you get, wow, 297 meters. That's very big, actually, right? You think about it, that's like, that's close to 1,000 feet. So some waves are enormous in terms of their size. 1,000 feet is the wavelength. So again, what you're saying is if you look at this wave, the distance between two adjacent peaks, that's your wavelength, right, is 297 meters, which is close to 1,000 feet. That's an enormous large wave. But look at the frequency. See how small that is compared to the X-ray. Much, much smaller of a frequency. And so what I'm going to do is I'm going to kind of give you a lowdown on all this, which is if you list out all of these types of waves, radio waves, I'm going to list them again, microwaves, infrared, I'll do IR for infrared, visible light, UV for ultraviolet, X-rays, and then gamma rays. Okay, those are our different types of electromagnetic waves. The radio waves have the lowest frequency. Okay, radio waves have the lowest frequency, but they have the longest wavelengths. Whereas you're going to increasing frequency, gamma rays have the highest frequencies. And they have the shortest, the smallest wavelengths. Okay? But remember, earlier on I told you that radio waves have the lowest energies. Let's spell it properly. Right? And that gamma rays have the highest energies. Okay? So that means that energy goes in the same direction as frequency. Right? So if you have the lowest frequency, you also have the lowest energy. If you have the highest frequency, you have the highest energy. So that means that energy and frequency are proportional to each other. So energy is proportional to frequency. But if you look at wavelength, it goes the other way, right? It goes lowest energy is longest wavelength. The biggest wavelength gives you the lowest energy. So that means that energy is proportional to 1 over wavelength. As wavelength gets longer, energy gets smaller. Okay, so those are two relationships we have to be aware of. We're going to talk about them next, which is to look at the relationship between energy and frequency and energy and wavelength. But the reason that frequency and wavelength follow this pattern is that if you go back to our equation here, this times this is a constant. So if this gets bigger, in order to maintain a constant, this one's got to get smaller, or vice versa. So whichever one gets bigger, the other one's got to get smaller so that when you multiply them together, the number doesn't change. So let me show you what I mean by that. Suppose I said, just to make numbers easy, suppose I said C is 1 and wavelength was 2. Well, in order for this to be true, the frequency would have to be a half, right? But if I said now that the wavelength is a half, then the frequency would have to be 2 in order to make it 1. So if this one goes down, this one has to go up, just so that they're equal to that. Okay, so that's your relationship. That's called an inverse proportion or an inverse relationship, where if one goes up, the other one has to go down to mathematically. Okay, so let me show you then the relationship between energy and frequency. So I won't go through the history. There's a lot of history in here, and it's all fascinating history. But essentially what happened was Einstein and Planck, Max Planck and Albert Einstein, they essentially figured out that electromagnetic waves, which again, we're going to use the word light to refer to electromagnetic waves, is constructed of particles, which we call photons. So if you actually take a light bulb and you look at the light that's coming out of the light bulb and you analyze that light, what you'll find is that it's waves. These are waves, but they're constructed of photons, individual particles. And these individual photons, I'm going to use a little symbol of like a little disk with a little wave symbol in there. I'll use that as a symbol for the photon. So your eyeball is actually very sensitive to these. So under really precise conditions, you can do this really interesting experiment where you make a room really, really dark and you put a light bulb in it, and then you put a person in there. and you train that person to see light coming from the light bulb, but you turn the light bulb so dim that it's capable of just giving one photon at a time, just one little particle of light. And what happens is you then, every time that you think you see a flash of light, you hit a little button. And it turns out that if you do that with people, some people can get it right about 55% of the time, a little bit above random. So that means that they are, in some sense, sensitive to individual photons of light. Okay, so pretty amazing. Human eyesight's really good. We really use our eyesight in order to be able to detect things and to sense things. So the photon is the smallest particle of light. It is a particle, but it has wave-like properties. This is sometimes called duality. It behaves like individual particles, but it also behaves as a wave. So that's the duality of it. And these are called photons. And each photon has an energy. And we'll use the symbol E for that energy. Photonic energy, if you want to call it that, the energy of a photon. Okay. The photon's energy is, again, notice it goes with frequency. Higher frequency means more energy. And so they're directly proportional. And I'm going to write the formula for it right here. The energy of one photon is simply h times the frequency. So, right, this is the frequency of the photon. So imagine this little particle that's moving through space, but it's also vibrating. It's vibrating at some frequency. It has some size to it. It has a wavelength. It could be a really small wavelength, or it could be a really large wavelength. But the energy is how many vibrations every second it's having. So if it vibrates really rapidly, it has more energy. If it vibrates more slowly, it has less energy. So AM radio waves, they vibrate relatively slowly, so they have less energy. Gamma rays and X-rays, very high frequencies, so they have a lot of energy. This little symbol H is a constant. This is called Planck's constant. And the accepted value for H is 6.626 times 10 to the minus 34 joules times seconds. Okay, that's the value of H. It's a constant. I'm not going to talk too much about Planck's constant. It's a fascinating constant. It has, the value of it has certain ramifications for our universe, but it is a very small number. Notice how small it is, 10 to the minus 34. The fact that it's so small is actually the reason that atoms behave very differently than people or planets. They have different properties based on the size, and that has to do with this Planck's constant. So what this tells us is there is a relationship between energy and frequency, and because there's a relationship between frequency and wavelength, that means there's also a relationship between energy and wavelength. So let me write those two relationships down, and then we'll take a look at a problem here. So the two relationships, one is between frequency and wavelength. And now we have a new relationship, which is energy equals H times frequency. But because frequency and wavelength are related, that means that energy and wavelength are related by this equation. So all I did here with this third one was I said wavelength is speed over frequency. So I put speed over frequency right here for frequency. I'm sorry, speed over wavelength. So now you have speed over wavelength over here. Okay, so these three equations, these are the three that we'll use for these types of problems. And then remember, we've got two constants. So you got to know these two constants, 2.9979 times 10 to the 8th meters per second. And then H is the second one, 6.626 times 10 to the minus 34 joule seconds. Those are our two constants. Okay. So let's take a look at a problem. Let's do red light. I'm going to use red light. So red light has a wavelength range. There's different shades. There's different hues of red, right? So there's the range right there. So there's different types of red light, 640 nanometers to 700 nanometers. So what I'm going to do is I'm going to pick one of those wavelengths. These are wavelengths. Notice it has meters in it. That's wavelength. So I'm going to pick 600 and let's do 670. Remember, the photon is the smallest particle of light. So let's say that you have a photon and it has a wavelength of 670 nanometers. So notice it has nano in there. You're going to see that a lot with visible light. Nano, 10 to the minus 9. Okay. So what I'm going to do is, because frequency is typically in hertz, I'm going to write this wavelength out in meters. So nano is 10 to the minus 9. So 670, 10 to the minus 9. Right? Nano is 10 to the minus 9. So 670 nanometers would be 670 10 to the minus 9 meters. So there's your wavelength. So for this, let's calculate the frequency of the photon. And then remember, frequency is nu. And then calculate the energy of the photon. Okay. Very simple. If we want the frequency, we can use this one right here, speed, frequency, and wavelength. So frequency would be speed over wavelength. Just using this one over here. So 2.9979 times 10 to the 8th meters per second. That's a constant. That's going to be the same every time. And then you have the 670 nanometers. Okay, remember, you want to have this in meters, convert the nano to meters. That way the units work out. So 2.9979 times 10 to the 8. That's a big number. Divided by 670 times 10 to the minus, that's a small number. A big number divided by a small number is a really big number. So you're going to get 4.4745 times 10 to the 14th. 1 over seconds, but again, 1 over seconds is hertz. Now that's a lot of sig figs. We really only have 3 sig figs. So I'll round that to 4.47 times 10 to the 14th hertz. So even visible light, which is sort of like in the middle of the spectrum, it has pretty high frequency. That's a pretty large vibrational frequency for red light. So then we want to find the energy of a photon of red light. I'll call it a red photon. There's no such thing as a red photon, but there's photons that have the frequencies that we perceive as red. Remember, color is a perception. It's not a real thing. Things don't really have color, but we perceive the frequency of photons as color. Okay. So the relationship there, if you're trying to find energy, is this one right here. E equals h nu. So that's 6.626 times 10 to the minus 34 joule seconds. And then your frequency, I'll use this one up here just to keep the sig figs in there. And then again, if you're doing these kinds of calculations, put it in seconds. So that way your seconds cancel. And so now you're going to get an answer in joules. So times 6.626 times 10 to the minus 34. And you get 2.96 times 10 to the minus 19. That's about right. The energy of visible light is usually about 10 to the minus 19 joules. Very small. Right? That's not, 10 to the minus 19 joules is not enough energy to even move a molecule. That's not enough energy to move a molecule. So that what that means is when we see light, and let's say light heats us up, we're getting warm because of the light, that's because so many particles of light are coming, moles of particles of light. So then it gets to be a pretty large number. If you have a mole of red photons, you can do some stuff with that. You can start moving things around. Okay, so two relationships here, frequency, wavelength. Typically, when you do the calculations, you want to have the frequency in 1/seconds, and you want to have the wavelength in meters. And then energy. Energy is related to frequency very simply, h times nu. If you want to use wavelength directly in the energy, we could have done that. We could have over here, we could have said energy equals hc over lambda. We could have put those two numbers in, and we could have put this number in. So we could have done that. And that would have given you the same answer. You would have got this one here. But I decided to go ahead and use this one directly. Okay. That pretty much gets you through the first two sections of chapter 6. So tomorrow what we'll do is we'll start looking at section 6.3. And if we have time, we'll look at section 6.4. This is going to connect electromagnetic waves to the atom, so we understand how they work with atoms. And then this 6.4, we're going to start getting into the quantum theory. Okay. So we're going to do a lot in this chapter. This is a really meaty chapter. We're doing everything from electromagnetic waves all the way to the structure of the atom. So it's a lot in here. Okay. So have a great day. Enjoy the warmth of wherever you're living, and if you're not out in the snow, and if you have to go out to work or go out to the snow, good luck, and I hope you're safe. Have a great day. Reach out to me today.
Great one.
Okay.
Thank you.
Take care.
Have a nice day.
Thank you.
Bye-bye.